Hello and welcome to another one of D's ADD videos. Today we're going to be looking at an example of points of inflection. So, just a quick recap. When we're finding relative extrema, we use the first derivative, set it equal to 0, use test points on either side of that critical number and your vertical asymptotes, and then that tells us the intervals that it's increasing and decreasing, and also allows us to determine relative maxima and relative minima. However, when we set the second derivative equal to 0, what we find are called possible points of inflection. Why are they possible and why aren't they actual points of inflection? Because you got to prove them to be an inflection point. So how does it become a point of inflection? How does it go from possible point of inflection to an actual point of inflection? Well, you have to set a test point on either side of the possible point of inflection into your second derivative and see if it's positive, concave up, or negative, concave down. Alright, so let's do all that. Here's our function. You take the derivative. You could have used the product rule here if you wanted to, but it's just easier to distribute that x squared through here to get this as your starting function. Okay. So now that you have your starting function, you derive it, okay, and you get this as your first derivative. Just bring down the power rule. If you were to do your tests, you would find that this is your relative max, this is your relative min, and it's increasing on this interval and decreasing on that interval. Alright? That's not what this video is about. This video is about the second derivative and points of inflection. So to take your second derivative, you go to your first, use the power rule again in this situation. Not too complex, I'm just trying to get the point across to you guys. There's your second derivative. And if you set it equal to 0, then you get your critical value, in this case called a possible point of inflection. So here is set equal to 0. That gives you 1 when you solve for x. So 1 is your possible point of inflection. Okay, it's like your critical point. Now there is no area in which the second derivative is undefined, so we don't have to worry about that. Usually if you have your original function undefined at a value, by the time it gets to the second derivative it's still undefined there, and you'll have to test on either side of it because it's an asymptote, a vertical asymptote. So here we have 1. If I plug in 0 as my test point, I get a negative concave down. If I plug in 2 as my test point, I get a positive value, so I get concave up. Okay, so now that I know that the concavity has changed, what conclusion can I make? Well, I can now say that 1 is a point of inflection. But remember, your answer has to be an ordered pair, so to get your y value, you have to go back to this original equation, plug in your 1, you're going to get 1 minus 3, it's a negative 2. So your actual point of inflection is 1, negative 2. Okay, so that's you plugging into the original. So now the intervals of concavity can be determined by this number line. From negative infinity to 1, it's concave down. From 1 to infinity, it's concave up. And that's how you would write it. Make sure, again, you don't use unions, use or semicolons here if you've got multiple areas or intervals. Alright, so that was a very, very basic example to get the ball rolling for you to be able to practice a few on your own. So more important than watching the videos, make sure you practice, practice, practice. Thank you and have a nice day.